Problem? What problem? All is fine with gfortran on Linux or Cygwin, and on Windows all is fine for static archive libraries with the .a extension. Quite often your Fortran library that you actually want won't use any common blocks, and so there's not a problem anyway. But some Fortran libraries, Tom's is quite a big one and quite a well-known one, do use common blocks, but only in a handful of routines out of hundreds. And you might want to use those routines in the first place. So all you have to do is list all the files that have the common blocks in them, and then you can find out which ones they are, and then you can find out whether you want them or not. And if you don't want them, well, just don't bother. Of course, if you did want them, or you wanted to put all of them into a library, you could put just the common block routines into a static library, and the rest of the routines that didn't use any common blocks into a DLL. However, if you're really unlucky and you really must have these common block routines in a Microsoft DLL, you can get around it using something called Fortran modules, and this is going to be introduced in the rest of this video. So I'm obviously assuming you're calling your functions in your Fortran DLL library from a program written in Fortran, as does the rest of this video, of course. However, in the next video we'll look at mixed language programming in the shape of calling Fortran from C or C++. And what we find is that this fixes the DLL data problem. You can get data in and out of your DLL function if you call it from a C or a C++ program. So there you are, you've got a DLL full of Fortran functions, you call it from C++, and everything works fine. So if you're naturally a C or C++ programmer in the first place, this is the best way to fix the problem. But for the rest of this video, we'll be looking at calling Fortran DLL functions from a Fortran main program. Well, we finished off our last video when we saw that our data wasn't getting into our DLL and it wasn't getting out of our DLL, and so the variables that were supposed to be like global variables in the main program were behaving like local variables. They weren't changed by any calls to function 1 or sub1. We should have mentioned that if we looked at our definition file, that indeed we see that fun1 block is exported as well as sub1 block. So it's not as if the export all functions is ignoring these common blocks. If we go to the GCC pages, we can go to mailing lists, and under mailing lists we see Fortran, and we can go for the subject index. I'll change it to this mailing list only for Fortran rather than have any particular time period, and then search under DLL export common. You see, what I did was created a directory called hello4, and this time used exclude all symbols and reintroduced those !GCC directives to see if I could do it manually. It ignores the export of the common block no matter which way I try. Anyway, it appears that this is a genuine bug in GCC and its version of Fortran, gfortran. Anyway, searching around there leads you to this gnu.org bugzilla, and this particular bug that if you try and do it manually using !GCC attributes, it doesn't work for common variables in procedures and block data. Now here we are I've copied the old Hello 4 to Hello 5, and I've now got a new Hello 4. The first thing you'll notice are these mod funds which weren't there before. These are modules. There you are, module mod sub 1, and amongst other things there are a newer way in which you can achieve the same thing as having global variables. All I've got in there is I'm declaring y sub 1 as real, 32-bit floating point, and doing save end module sub 1. Of course this is just a comment, and the same thing for mod fun 1. Declares a real variable y fun 1 and does a save end the module. Nothing else. Modules can be very complicated things, but this is about as simple as you can get. Meanwhile, back at the makefile, you'll see that I've compiled them like this, gfortran -c mod sub 1.f, and these produce those .mod files. And I've also included modfun 1.0 and mod sub 1.0 into the library. Here we are back in program hello. I've stripped out those common statements altogether, and I've said use mod sub 1, use mod fun 1. That's the way that you actually include those modules into the program. Here we are, for instance, in the function fun1. Again, I've stripped out the common statements altogether, and I now have just use mod fun1. You can see that I'm using that variable y fun1 where I used to use y. You'll remember that fun1 was dependent upon a function fun2 that also had a common block in. So we've stripped that out, and we've done use mod fun1, and again we have y fun1 which gets incremented by 202, and the other write statement with y fun1. And we've done the same thing with sub 1. We've stripped out the common blocks and replaced them with the modules. Well, I've rebuilt the DLL, including the modules, and lo and behold, I can now compile hell DLL, and everything works fine. Everything is as it should do, and y fun1 ends up as 322.5. After calling sub 1 in the main program, we can see that y sub 1 is now 8.05, so that's been incremented properly. It's left sub 1 here and printed out 8.05, so everything has behaved as it should have done. Well, suppose we're going to have to hack our library function and remove all the common blocks. Well, the library function could have a dependency within the library, so the library function that you're calling depends on dep1 and dep2, for instance, but it could be dep3, dep4, dep5, and so on. And just as fun1 depended on fun2, the dependencies can have dependencies, and in fact we could even have these things calling other library functions on which they're dependent, and they could all have that common block or multiple common blocks in them that you want to remove. This could be a very, very nasty task, and it's also quite fraught with difficulty in the sense that it's going to be very easy to introduce mistakes into your library, and you'll either get garbage out, the thing will crash, or even worse, you'll get plausible looking results which are in fact wrong. Well, we've gone back to using modules, but this time we're using common blocks within the library as well. So for instance, if we go to sub 1, here we are, sub 1 block Y just as before, but now what we're doing is we're setting Y, we're copying the data, if you like, in Y sub 1 to Y, and then copying it back again. The same thing goes for fun1. We've still got our fun1 block. Nothing has changed in fun1 apart from the y equals y fun1 statement at the beginning and y fun1 equals y at the end. If we look at fun2.f, we've not changed it at all. So if we go back to, let's say, fun1, what we see is we haven't changed anything at all. We haven't got rid of common blocks or anything. We haven't changed variable names. We've still got y all the way through as we had in the original common block program. And all we've done is we've introduced these two statements, y equals y fun1, which gives the initial input to y. Here we have y equals y fun1, so we copy the global data to y. Y never gets out of the library, and then y fun1, the global variable, becomes the end result y. So this is a way in which we have a minimal amount of change. You can see here it's worked perfectly well, and I just noticed that I had a y fun1 instead of y sub 1 there, which is why there was the wrong answer earlier on. So let's save that, and you can now see that beta is 8.05, so it's been incremented as it's supposed to be. So if we are going to make changes to our library functions, this is an easier way to do it and a less dangerous way to do it. But these copies here, you could have a lot of things in the common block that might be very large matrices, for instance. I guess you could get round that using fortran pointers. Otherwise you'd actually have large loops copying data and also a lot of extra memory. Of course you might have so much RAM that you don't really care and you wouldn't have to do that, but anyway, copying a lot of data at the beginning and the end might be somewhat problematic, and that might be overcome by the use of pointers. I don't know how at this point. So what would we do if we had a real library? Well, first of all, we'd keep the original sub1.f and fun1.f and copy them to my fun1.f and my sub1.f. Here we are, for instance, in my fun1.f. We'd make our alterations here, and fun1.f would be the original. We wouldn't touch that at all. Then over in the makefile, we build a static library with the originals. Here we are, libhellostat. Right, we would then build the dynamic library, mysub1.f and myfun1.f. Here we are, and we'd give instructions to compile either or both sub1.0 and mysub1.0, fun1.0 and myfun1.0. So we've got the static library calling the originals and the dynamic library. After all, it's only the dynamic library that needs the changes. And then, as well as hello.f, I'd have hello.dll.f, and that calls the mysub1.f and myfun1. So in this way we have the original library and the static library compare the results of the original library with the DLL, so you could see if we've managed to introduce any mistakes when we've altered myfun1 and mysub1 from the original copies.